Hey guys, my name is IBM and I'm welcoming you to my YouTube channel. Today I would like to take you to the last lesson of waves and superposition. This is going to be lesson 15, I think, and we shall basically be talking about the diffraction grating. I think the diffraction grating is going to be the last lesson in waves and superposition. Do not forget the course outline of the topics you're supposed to cover by the time you finish your AS. You must have covered these topics: physical quantities and units, errors and uncertainties. By the way, I've recorded solved past paper questions under errors and uncertainties, treatment of uncertainties, so you should always check them out. Kinematics, dynamics, force, density, pressure, work, energy and power, deformation of solids, waves and superposition, electricity and DC circuits, and then particle physics. These are the topics you're supposed to cover by the time you finish your AS. And currently we are finishing up with waves and superposition, and this is going to be lesson 15, diffraction grating. So having seen a lot of concepts under waves and superposition, we have already seen standing waves and stationary waves. We have already seen the concept of diffraction of waves, which was the spreading of waves into regions of geometrical shadow. We have already seen interference, especially we have seen a two-source interference where waves were overlapping, resulting into a given displacement or a given amplitude, where we had both constructive and destructive interference. And we are currently going to see diffraction grating. Remember in lesson 13 and 14, we talked about a Young's double slit experiment or Young's double slit, where in lesson 14 basically we concentrated on Young's double slit equation. So in lesson 15 we are going to concentrate on the diffraction grating and the concepts around diffraction grating. Okay, so let's go. So this is going to be 8. It is supposed to be 8.4 diffraction grating, but it depends on what your teacher or how your teacher structured his teaching style. So it may not always be the same style. So what is a diffraction grating? So diffraction grating, we have having seen the double slit and having seen the double slit experiment. A diffraction grating is also similar to the slide used in the double slit experiment. The only difference is that this one has many slits rather than just two that were mentioned in the double slit experiment. So you can think about a diffraction grating as an extension of a double slit, but instead, this does not only have two slits, it has many more slits, thousands of slits in a given meter, or thousands and thousands of slits in a given meter. In your school laboratory, you should be seeing things like these. These are called a diffraction grating. They are labeled, for example, this one is 1,200 lines per millimeter, which means in 1 millimeter there are 1,200 lines or slits. Instead of calling them slits, we shall call them lines because they are very, very tiny and very close to each other. You could also be seeing 600 lines per millimeter, 300 lines per millimeter, and so on and so forth. Of course, when you look at the plastic material here, you may not see the lines with your naked eyes unless you use a microscope, but there are infinitely many lines here. So of course, the many slits or the many lines onto this plastic material or onto this slide also makes this diffraction grating different from a double slit in terms of intensity. Because if there are more slits, we would expect that more light goes through goes through the more light goes through the grating as compared to the double slit which had only two slits. So diffraction grating is similar to the slide used in the double slit experiment, but this one has many more slits than just two. A diffraction grating consists of a large number of they are identical, very closely spaced slits, or we shall just call them lines, which have been rolled on a glass or plastic plate like this one here. Thousands of lines have been have been rolled on this plastic material, which may not even be seen by our naked eye. So these lines can only be drilled or can only be rolled through this plastic material using a machine. So there are many lines. There may be as many as 10,000 lines per centimeter. Each line is capable of diffracting the incident light. So each line is capable of diffracting the incident light which is incident onto the diffraction grating. And therefore, most likely what would be seen on the screen if we had a screen may be the image of this slit because of this line, because each line is capable of diffracting the incident light so that it spreads until it reaches the screen. So we now know what a diffraction grating is in contrast to a double slit. It is like a double slit because even a double slit could be made from a plastic plate or a glass plate. So it could be like a double slit. Unfortunately, the difference would be that this one has thousands of lines which have been rolled on this plastic plate or on this glass plate, so that these lines are very close to each other. And since there are many, we shall later on be talking about the intensity being high because more light could go through since there are so many slits onto the plastic plate. So if monochromatic light is incident on that plate or on the diffraction grating, we are going to see a pattern of narrow, bright interference fringes. We have already seen interference in lesson 13 and 14. So we are going to see a pattern of narrow, bright interference fringes. These ones are the ones which are visible on a darker background. So these interference patterns will appear on a screen if a screen is placed on the other side. So let us assume we have monochromatic light. Of course, monochromatic meaning a single color or a single wavelength, going through a plastic plate which has thousands of slits or thousands of lines, which we call the slits. So these lines diffract light and as it passes through the grating, and this will result into interference patterns which are going to be seen on the screen. So if we analyze or if we look at the screen, if the monochromatic light was red, we would see interference patterns which would look like this on the screen. We would see interference patterns whose intensity decreases as we move away from the center. So it's like interference patterns are formed on both sides of the center, and these interference patterns have their intensity decrease as you move away from the center. So these interference patterns are actually patterns formed as a result of constructive interference, and therefore they are going to be called bright fringes. So it is usual to measure the angle theta at which they are formed rather than measuring their separation. Remember, for the double slit, we measure the separation x. For a diffraction grating, we shall easily measure the angle theta at which they are formed. The reason being, these may not be formed at equal distances from each other. Therefore, the separation x may not be the same. And therefore, we cannot easily measure the separation x, but it is rather better for us to measure the angle theta. After all, even the angle theta is bigger and is going to be easy to measure with a good precision or with a good accuracy, if I can put it like that. So with the double slit that we saw earlier on, the fringes were equally spaced, and the angles for the double slit were very small or very, very small. But with the diffraction grating, the angles are much greater. The angles are bigger and the fringes are not equally spaced. Like I've said, the fringes are not equally spaced. The bright spots will not be equally spaced. And that's why it is even hard to see them clearly or to see many of them on a flat screen. So that's why here I demonstrated this with a curved screen. If we want to see many of them, we must have a curved screen. So with the diffraction grating, the angles are much greater and the fringes are not equally spaced. So these fringes, because they are bright fringes which are seen on the screen, these fringes are going to be called maxima. They are as a result of constructive interference. So we may not always talk about dark and bright fringes. For diffraction grating, we shall only talk about the bright fringes or the bright spots or the maxima. At the center, where all light from the different slits travels the same distance, like we saw with the diffraction with the double slit, we form what we call the central maximum. The central maximum or the zeroth order maximum, where the angle theta is going to be 0, or the angle of diffraction theta is going to be 0. Then this will be followed by the first order maxima either above or below, to the left or to the right. So the central bright fringe or the central maximum is surrounded by several other orders above and below. So following with the first order, second order, and so on and so forth, both above and below, or to the left and to the right. So this pattern or the pattern is symmetrical. So there are two first order maximum, two second order maximum, and so on and so forth. So for diffraction grating, we expect symmetrical interference patterns where there will be a first order on the left, a first order on the right, a second order on the left, a second order on the right, on the right, and so on and so forth. So they are symmetrical, or they are centered at the central bright fringe, or they are surrounding the central maximum, which we call the zeroth order maximum, where the angle of diffraction is 0 because light from all the different slits is going to be traveling the same distance to reach the center onto the screen. So light from different slits travels the same distance to reach the center on the screen, and therefore in that case we say the path difference is going to be 0, and when the path difference is 0, it means the phase difference is also 0. This results into constructive interference here, which forms the bright spot of the 0th order maximum. That is a diffraction grating. Of course, you should be able to demonstrate this in your class with your teacher. If you have a diffraction grating and you have a laser, this can easily be seen in class. Of course, you need a darker room to be able to see this clearly. Let's first obtain the diffraction grating equation, or talk about the diffraction grating formula. You remember the double slit equation, which was lambda equals to ax divided by d. Lambda equals to ax divided by, this was the diffraction grating, this was the double slit equation. Now, for diffraction grating, we shall be talking about this expression here, this sine theta equals to n lambda. So let's consider a smaller section of a diffraction grating where only a few slits have been magnified and shown on the screen here. So let us assume monochromatic light of wavelength lambda is incident on a diffraction grating, and we are going to assume that the distance between two slits is d. So if I use a magnifying glass to magnify between two slits, I've magnified between two slits, and this is what I have. So when you magnify between two slits and very close to the slits, you will notice that it appears as if these rays are going to be parallel, especially if they are forming interference patterns on a screen which is very, very far. So in other words, the separation of the slits is much, 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 much smaller than the distance between the slits and the screen. And if that is true, when you come very close to the slits, and the slits are very, very close to each other, so if we use a magnifying glass, it would appear as if the rays from the slits are parallel to each other. So these rays are almost, they are appearing to be parallel. Therefore, if I try to find the path difference of course, this one is traveling a shorter distance than this one. So the extra distance which this one moves, let me say this is R1 and this is R2. So this is going to be R1 and this is going to be R2. So R1 is traveling an extra distance than R2 to reach the point where they undergo interference. So the extra distance they move is going to be this distance here. The extra distance R1, light from following R1 moves compared to light following R2, is going to be that distance there, which we call the path difference. We call this SC, we call this the path difference. And since interference maxima are being formed, this path difference is given by n times lambda, that is for constructive interference. So mathematically, if this angle is theta, this angle is theta, it doesn't require to be a genius to know that, of course, all these angles are going to be, this angle is going to be theta, theta, theta. And mathematically, if this angle is theta, I think it makes sense for us to say that this angle is 90 minus theta. So this is 90 minus theta. And because this is already 90, so it makes this angle theta the angle sum of a triangle. Of course, theta is the angle of deviation from the original path of the incident beam. So the dotted line is showing the incident direction of the light, but then it has undergone diffraction, so it has deviated. So the theta is going to be the angle of diffraction, which is the angle through which the light has deviated from its original path. So if this angle is theta, this angle is going to be 90 minus theta, because the whole of this is 90, the whole of this is 90. So if the other one is, the small one is theta, then this is 90 minus theta. But this is a projection which makes 90 degrees with the other one, so it means this is going to be theta, because the angle sum of the whole triangle should be 180. So a parallel rays of monochromatic light of wavelength lambda are incident on a diffraction grating in which the slit separation, I've called it D. Let us assume the grating has n lines per meter. N is equal to the number of lines per meter. This is very, very important. If it has n lines per meter, so it is going to be hard for us to measure the distance D, because the distance D is going to be very, very, very small. But if we know the number of lines which are on 1 meter, or the number of lines which are in 1 meter, so it means the distance between the two successive slits, which we shall call the line spacing, can simply be got from the reciprocal, or 1 divided by n. So instead of measuring the distance between two slits, which is going to be very hard because it is very small, which will give a large percentage uncertainty, then we would simply just divide 1 by the number of lines onto the number of lines on the plate. For example, we have n lines in 1 meter. So we shall just say 1 divided by the number of lines in 1 meter to get the distance between the two successive slits, or two slits. So constructive interference only occurs along a few precise directions, one of which is shown in the diagram that we have just seen. So constructive interference is the one which occurs. That's why we had maxima being formed, and for that reason we shall be considering constructive interference, and that's why I say the path difference. The path difference is going to be n times lambda, where n is a whole number and lambda is wavelength. So let us try to derive the equation d sine theta equals to n times lambda. So we are going to consider the magnified section of the diffraction grating, where we have already seen that if this angle is theta, the angle of diffraction was theta. So it means this is 90 minus theta, which, because this was 90, it made this one theta. Remember, I said this is the extra distance which light from the upper slit travels to meet with light from the bottom slit. And this extra distance, we call it the path difference. So SC is going to be the path difference. And if you consider this right angled triangle here, with this angle here being theta, you notice that SC is going to be the opposite. And of course, BC is going to be the adjacent, and AB, which is D, is going to be the hypotenuse. So since SC, we know that SC is the path difference, which is equal to n times lambda, and we know the hypotenuse, which is D, so it means we shall use sine of theta equaling to the opposite, which is SC, divided by the hypotenuse, which is AB, which is actually D. Remember, the path difference SC for constructive interference is given as n lambda. So we can say that sine of theta is equal to n times lambda divided by d, which means that n lambda is equal to d sine of theta. This will always be called the diffraction grating formula, and it's the one you'll always use many times in the exam. So light from A must be in phase with light from B. That means constructive interference is going to happen. And this can only happen when the path difference is a whole number multiple of the complete wavelength. In other words, path difference is n times lambda, where n is a whole number. If we assume that the screen is far away from the two sources and the wavelength is very, very small, therefore the waves are approximately parallel as we have seen above. So the lines which I have drawn here in red are approximately parallel if the screen is far away from the source or from the slits and the wavelength is very small. So very close to the slits, the rays would appear parallel. So we have already seen that the path difference SC is going to be n times lambda, where n is a whole number. And if we use trigonometry, we have already seen that sine of theta is going to be SC divided by d, which implies that S is going to be d sine theta. So it doesn't take you to be a genius to see that d sine theta equals to n lambda. So what is d? D is going to be the slit separation, or the distance between successive or adjacent slits, or the slit separation, which is the same as we have seen that d is equal to 1 divided by n. As long as we know the number of lines per meter, then we can easily find d. It may not be easy for us to measure d using a ruler or whatever, because d is very, very small. Then theta is going to be the angle of diffraction, which is measured from the central maximum. So theta is always measured from the center. The angle of diffraction, which is always measured from the central maximum. And then n is a whole number, which is the spectrum order, or the order number that we shall be talking about, order of diffraction. Order number or order of diffraction. So we have zeroth order, which is the central order maximum. We have the first order, second order, third order, and so on and so forth, both above and below the center. Then n could be equal to 0 when sine theta is equal to 0, and theta is also 0. This gives the straight on direction, or what we call the zeroth order maximum. So when n is 0, we have the zeroth order maximum, because sine theta will be 0, the angle of diffraction will be 0. And I said in that case, light from the different sources is traveling equal distances to reach the center. So we form what we call the zeroth order maximum. And when n equals to 1, we shall have what we call the first order. When n equals to 2, we shall have what we call the second order, and so on and so forth. So that is how a diffraction grating is going to behave. Okay, so let us understand this even in more details. So the figure below shows maxima in the diffraction pattern of a diffraction grating, as we have already seen. There will always be a zeroth order, first order above, first order below, second order above, second order below, third order above, third order below. But I want you to notice that when you look at this diagram, it's like there is a limit. This is the diffraction grating. So it's like there is a limit on the number n. N has a limit. It is not infinite. N has a limit. N will have a limit. But before we look at the limit, so the orders move like that. Unfortunately, because all the light travels the same distance to reach the center to form the zeroth order maximum, at the center we have the brightest spot. So the brightest spot will be found at the center. And so that means the central maximum has the highest intensity, because brightness is related to intensity. So at the center here, where we have the zeroth order maximum, the intensity is also maximum, or the intensity is highest, but the intensity decreases as you move either to the other side or to the other side. So the intensity decreases. And if I was to sketch a graph of intensity against the distance from the central maximum, so it means the graph would look somehow like this. The intensity goes on decreasing, but of course, both orders or identical orders will have the same intensity. So if this is first order onto the left, this will be first order onto the right. These have the same intensity, and the intensity goes on decreasing. This could be maybe the second order, the other is the second order on the other side. So as you move away from the center, the intensity decreases. So intensity decreases as you move away from the center. So it means the zeroth order is going to be the brightest. The brightest order is going to be the zeroth order. And if we look at this equation, sine theta, this sine theta equals n lambda, mathematically we know that sine theta has a limit. Sine theta can never be greater than 1. The greatest value of sine theta is going to be 1. And when sine theta equals to 1, it means the theta is equal to 90 degrees. So there is a limit to the number n of the spectra or orders that can be obtained. Because we know that if sine theta is, the maximum value of sine theta is 1, when the theta equals to 90 degrees, it means n is maximum. We have reached the maximum order. So we can't form orders to the left of the grating. The maximum is when theta equals to 90 degrees. So it means the number n has a limit. And also do not forget n must be a whole number. The number n has a limit and n must be a whole number. So let's first compare the diffraction grating and a double slit before we go to examples. So diffraction grating has an advantage over the double slit method of measuring wavelength in that for diffraction grating it has many slits, and of course many slits are going to be better than just 2. Why are many slits better than just 2? So with a diffraction grating, the maxima are more sharply defined than for a double slit. In other words, the brightest spots are more sharply defined than those formed in a double slit. Or to modify this even further, with a diffraction grating, the maxima are also very, very bright. And why are they bright? This is because the beam passes through more slits than just 2. Therefore, the intensity of light is high. More slits means more light going through the plate, and therefore the intensity of light reaching the screen is going to be higher. Therefore, we say the maxima or the brightest spots formed on the screen are even brighter because the intensity is high. With the diffraction grating, we have seen that the angles are large, so they can be measured with a greater precision. And I said whenever a quantity being measured is big, the percentage uncertainty is small. So because the angles considered in a diffraction grating are large, they are easily measured with a greater precision. So the percentage uncertainty is very low. However, with the two slits, we have automatically, we must measure the slit separation. And the slit separation is very small. That's number one. And therefore, we have no any other option because there are only two slits. Yet for diffraction grating, we have thousands of slits per meter. So if we know if we know the number of slits in 1 meter, for diffraction grating, the separation of slits was just d equals to 1 over the number of slits. Yet for diffraction grating, the separation of slits A must be measured using either traveling microscope, or of course we may not easily use a ruler because the ruler may not be precise enough because these slits are very close to each other. So we may use a traveling microscope. So because A is very small, it is hard to measure. So with two slits, there may be a large inaccuracy in the measurement of the slit separation A. The fringes are close together, so their separation may also be measured imprecisely. Yet for diffraction grating, if we know that in 1 meter there are n lines or n slits, the slit separation can be just got from 1 over n. So it means d is more precise than A. D for diffraction grating, which is slit separation, is more precise than A for a double slit, which is also slit separation. So I said for diffraction grating, the angles are large. And by the way, for double slit, the fringe separation is not also that big. So even measuring it brings in another challenge of inaccuracy. Okay, so all along we have been considering monochromatic light, light of the same color, single frequency or single wavelength. Suppose the light incident on a diffraction grating is white light. Remember what we saw with the white light on a double slit. It's almost the same thing we expect to observe with the white light on a diffraction grating. Since for diffraction grating, d sine of theta equals to n times lambda. If white light is incident on diffraction grating, it means d is the same for all the 7 colors that make up white light. So for the first order, we could think of n being equal to the same, but note that sine theta is going to be directly proportional to the wavelength. Since white light is made up of different wavelengths, it means each color may undergo a different angle of diffraction. So what is the effect? Each color is most likely going to form its own pattern. However, at the center where theta is 0, all the colors travel the same distance to reach the center. So it means the path difference will be 0 for all the colors. And since the angle of diffraction is 0, it means at the center all the colors will combine to form back white light. So if white light from a source is incident onto a diffraction grating, at the center we have a white spot, which is going to be the 0th order. So this is for n equals to 0. Unlike the double slit where the white spot was surrounded by dark fringes on both sides, here the white spot is now surrounded by bright fringes or colored fringes on both sides. And with the red, because red corresponds to the longest wavelength, from red, Richard of York gave birth in vain. These are the 7 colors. So red has the longest wavelength, so it undergoes the biggest diffraction. And remember, the angle of diffraction is always measured from the center. So it means the red color will always be farthest from the white central maximum. So if at the center we have the white spot, it means we shall have patterns of the different colors surrounding the white spot, with the red being farthest. That's why we start with violet closest to the white, followed by indigo, followed by blue, followed by green, followed by yellow, followed by orange, and then red. Because red corresponds to the longest wavelength, it undergoes more diffraction. It has a bigger angle of diffraction. And because the angle of diffraction is always measured from the central order or from the center, then it means red is going to be farthest away from the central white spot. Mark the difference between this pattern with the one which was formed by a double slit. For a double slit, we had a central white spot which was surrounded by darker fringes, or which was surrounded by dark fringes on both sides. If it was a double slit, we would have a darker fringe on the left and on the right of the white fringe. Then now we shall have the pattern of the colored fringes. But for a diffraction grating, we only have a white spot which is surrounded by, we don't have the darker fringes here seen. So we have a pattern with a central white spot or a central bright fringe, which is surrounded by colored fringes on both sides, ranging from violet to red in that order. So if white light is incident on a diffraction grating, each wavelength which makes up or making up white light is diffracted by a different amount as given by this equation here. Because d is the same for the white light, for all the light, if n is the same, that means the angle of diffraction will depend on the wavelength. So because each color has a different wavelength, it will undergo different angle of diffraction. Remember, this splitting of white light is what you call the dispersion in IGCSE. And since we have said that red light has the longest wavelength in the visible spectrum, and therefore is diffracted through the greatest angle. So theta is the greatest for red light. Because violet has the shortest wavelength in visible light, and it is therefore going to be diffracted least. It has the smallest angle of diffraction. So thus we can simply conclude by saying white light is split into its component colors, producing a continuous spectrum. So this is what we call a continuous spectrum, a range or a band of diffraction patterns or a band of 7 colors forms what we call a continuous spectrum. Of course, you notice that there is no very clear boundary between each of these colors. They kind of overlap. As one fades out, another one comes in. So you cannot draw a clear boundary between these colors. So this is going to be the diffraction pattern of white light. You should be able to explain the diffraction pattern of white light. So if white light is incident on diffraction grating, each wavelength making up white light is diffracted by different amounts. The net result would be a central white spot or a central white fringe, which is surrounded by a continuous spectrum of the different colors, with the violet closest and red farthest, because red has the longest wavelength. It undergoes, or it has the greatest angle of diffraction. Okay, so when clearly viewed on a screen, this is exactly what we would observe. The spectrum is repeated in different orders of diffraction as shown. So on the previous slide, I just showed one order above and below. So we have a white spot. Here we have white, or the zero order white spot, which is now surrounded by the first order of the 7 colors, with red always being farthest. Then followed by the second order of the 7 colors, with red always being farthest. So the spectrum is repeated in different orders of diffraction as shown below. But not many of these orders will be visible on the screen. Just a few of them will be visible or will fit on the screen. So a 0th order white maximum is observed at theta equals to 0 because all waves of each wavelength are in phase in this direction. So at the center here, all waves are going to be in phase. An important use of diffraction grating is in an instrument we call a spectrometer, which is a piece of apparatus used to investigate spectra. If we can measure the angle at which a particular diffracted image appears, then the wavelength of light producing that image may be determined. If only we can measure the angle of diffraction, then from d sine theta equals to n times lambda. If I know that the image is appearing from or is appearing on the first order on the screen, then it means n is going to be 1. So if I can measure theta and I know the number of slits in the diffraction grating, I know the slit separation d, then I can find the wavelength. So by measuring the angle at which a particular diffracted image appears, the wavelength of the light producing that image may be determined. That is how a spectrometer works. I don't want to go into the details of a spectrometer in the AS curriculum. Thus, a diffraction grating is a simple way of separating white light into its constituent wavelengths. So a diffraction grating can easily be used to measure wavelengths. That's why in astrophysics and cosmology, when astronomers are studying the universe, you notice that light from a distant galaxy is passed through a diffraction grating and then it is analyzed to obtain the wavelength of this light. Of course, by measuring the angle of diffraction of a given beam of light, or by measuring the angle of diffraction of a given wavelength of light, astronomers can be able to analyze the wavelength and notice that the wavelength is maybe higher than the normal wavelength known in the laboratory, and therefore can come to a conclusion that maybe the universe is expanding in what we call the redshift. So thus diffraction is a simple way of separating white light into its constituent colors. So that is a diffraction grating. The most important takeaway is the equation or the diffraction grating equation, and then the diffraction patterns for white light. Examples. Monochromatic light is incident normal on a grating 7.0 times 10 to the power of 5 lines per meter. Of course, meter is a SI unit, so if it is lines per meter, so I know that this is capital N. Now, of course, I know students are always going to confuse capital N and small n. A second order maximum, so small n is going to be equal to 2. Second order maximum is observed at an angle of diffraction 40. So this is going to be theta. Calculate, remember theta is always measured from the center, from the central order maximum. Calculate the wavelength of the incident light. So we want a wavelength of the incident light. So remember d sine of theta is equal to n times lambda. And we have already mentioned that d is equal to 1 over n. So we want to find the wavelength. So d is 1 over n, which is 7 times 10 to the power of 5. Sine of theta, which is 40, should be equal to n, which is 2 times wavelength. So I just press my calculator. Sine of 40 divided by 7 exponent 5. Then I divide by 2. So this is giving me lambda as 4.59 times 10 to the power of minus 7 meters. So that is the wavelength. So the slits on a diffraction grating are created by drawing parallel lines on the surface of the plate. The relationship between the slit spacing d and the number n of lines per meter, we have already got this as 1 over n. And then using the equation, d sine theta equals to n lambda, or n lambda equals to d sine theta, we just make lambda the subject, and then we obtain this value here. Of course, when I change 4.59 times 10 to the power of 7 meters, minus 7 meters, to nano, I divide by 10 to the power of minus 9, which gives us 459 nanometers. Example 2. Most of these are easy, so I will not solve all of them. I'll just give a hint where possible, because we're just using the same equation, n lambda equals to d sine of theta. I normally don't solve this for my students. Monochromatic light is incident normal on a grating with 5 times 10 to the power of 5 lines per meter. A third order maximum, so small n equals to 3, is observed at an angle of diffraction 78. So this is going to be theta. Calculate the wavelength of the incident light. So this is similar to the previous example. I will not solve that. You just substitute in that equation. Remember, d equals to 1 over n. This was capital N. Light of wavelength 5 times 10 to the power of minus 7 is incident normal on diffraction grating. So you have the wavelength. Diffraction grating with 8 times 10 to the power of 5 lines per meter. So this is capital N. Calculate the diffraction angle of the first and the second order diffraction images. So we want to find the theta for the first and the second order. So you will find theta 1 when n equals to 1, and you will find theta 2 when n equals to 2. So just substitute in that equation. I don't think that is very hard. It is almost the same as this, as example number 1. Light of wavelength 590 nanometers is incident normal on a diffraction grating with the spacing 1.67 times 10 to the power of minus 6. So we have the wavelength as 590. We have the spacing. When they say spacing, that is now d, small letter d. how many orders of diffraction maxima can be obtained? How many orders? So we want the total value of small n, total n. So of course I will make n the subject. N is going to be d sine of theta divided by the wavelength. So d is 1.67 times 10 to the power of minus 6 times sine of theta. Of course, if for n to be maximum, sine theta is going to be equal to 1, or theta must be equal to 90 degrees. Remember we said capital small letter n, or the number of orders, has a limit, and the limit depends on sine theta, which has a limit as 1. Sine theta has a limit as 1, that is when theta equals to 90 degrees. So I will say this is times sine of 90 divided by the wavelength, which is 590 times 10 to the power of negative 9, because it was in nanometers. So this gives us 1.67 exponent minus 6 divided by 590 exponent minus 9. So this is giving me 2.83 and so on and so forth. Remember I said n must be a whole number. So if it is 2.83, we cannot round off. We cannot round off this to, you can't round off this to 3, not at all. So this rounds off to 2. It means the other order cannot fit on the screen. Now if this is the screen, we have the central order maximum. Then we have, this is for n equals to 0. Then we have n equals to 1. And we have n equals to 2. Of course, we have also these orders on the other side, n equals to 1 and n equals to 2. So depending on the examiner's question, how many orders? Of course, it could be 2 could be the answer if we don't add this 0 order and we don't add the orders on one side. But if the examiner asks for the total order of diffraction, total number of orders of diffraction formed, so this would be 1, 2, 3, 4, 5. So it could be 5. If all orders are considered, including the 0 order, the first order on the left, the first order on the right, the second order on the left, the second order on the right. So it could be 2, depending on the examiner's question. It could be 3 if the central order is considered. It could be 5 if all the orders are considered. So in many cases, it is always 2 plus 2 plus 1, or twice n plus 1. If n is 2, so it is 2n plus 1 for the total. Okay, you will see such questions many times in the exam. Monochromatic light is incident normally on a diffraction grating having a 300 lines per centimeter. So if there are 300 lines in 1 centimeter, so what is n? Remember, capital N should be the number of lines per meter. 1 centimeter has 300 lines. It means 1 meter will have 300 times 1 meter is 100 centimeters, so times 100. So this is the number of lines per meter. So it means now I can find d as 1 over n. So d could be 1 divided by 30,000. So that would be my value for d. The angular separation of the zeroth and the first order maxima is found to be 10. So theta is 10, because theta is always measured from the center. Calculate the wavelength of the incident light. So now we just substitute in the formula. So wavelength is going to be d sine of theta divided by n, because n was, they said, the zeroth and the first order, so n is 1. So this is going to be divided by n, so I'll just substitute. Where there is d, I'm putting 1 over 30,000 sine of 10 divided by n, which is 1. So I have sine of 10 divided by 30,000. So this is 5.79 times 10 to the power of minus 6, I think. Let me check it again. Sine of 10 divided by 30,000. So it's 5.79 times 10 to the power of minus 6 meters. I doubt if it gives 508. I doubt this, but you can check. I don't think it is 580 nanometers, especially when it is nanometers. Let me try to divide by 10 to the power of 9. It is 5800. There will be another 0 here. Okay. A diffraction grating has 300 lines per millimeter. Remember, 1 millimeter is 1,000 meters, so it means capital N is going to be 300 times 1,000. So that then we have this capital N is always the number of lines per meter. So that means if you wanted to find the separation between the slits, it should be 1 over N, which would be 1 divided by 300,000. That's the slit separation in meters. When it is illuminated normally by light of wavelength 530 nanometers. So this is the wavelength 530. What is the angle between the first and the second order maximum? We want the angle between the first and the second order maximum. So for the first order, small n is equal to 1. So what is theta? Remember, n lambda equals to d sine of theta. So I'll call that one theta 1. So sine of theta 1 is going to be n is 1 times the wavelength, which is 530, times 10 to the power of minus 9, divided by, I'm making sine theta the subject, so I divide by d, which d is 1 over 30,000. I mean 300,000. So it means sine of theta 1 is going to be equal to the 300,000 goes up. So it is going to be 530 times 10 to the power of minus 9 times 300,000, which gives me, I'll just press my calculator to find theta 1. Theta 1 is going to be 530 exponent minus 9 times 300,000. Then I get the sine inverse. So theta 1 is 9.15 degrees. Then it means the theta 2, it means the sine of theta 2. I'll just replace where there is n equals to 1, I'll put there n equals to 2. So it will be 2 times 530 times 10 to the power of minus 9, then times 300,000. So which implies that theta 2 equals to, so I'll just say 530 exponent minus 9 times 2 times 300,000. Then I get the sine inverse of the answer. So theta 2 is equal to 18.54 degrees. So we want the angle between the first and the second. So if this is the diffraction grating, this is the center, and this is the screen. So we have the first and the second. So we want the angle between them. This is the angle I'm looking for. I'll call this angle alpha. Remember, theta 1 is measured from the center. Theta 2 is also measured from the center. Then the angle between the two is alpha. So that angle is going to be, the angle I'm looking for is going to be equal to 18.54 minus 9.15. 18.54 minus 9.15, which is 9.39. So I think that is correct. So what is the highest maximum that can be obtained? That is the maximum value of n. Remember, we said when n is maximum, sine theta is equal to 1. Whenever n is maximum, sine theta is equal to 1. So n equals to d sine of theta divided by wavelength. Sine theta is equal to 1. D is 1 over 300,000. Then I divide this by wavelength, which is 530 times 10 to the power of minus 9. So 1 divided by 300,000 divided by 530 exponent minus 9. So this is giving me 6.29. N equals 6.29. But remember, we said n must be a whole number, so n should be 6. So the highest maximum that can be formed is the 60th maximum. Remember, n should be a whole number. If they wanted total number of orders, then it should be 6 plus 6 plus 1. Because remember, we said there is a central order where n is 0, which is also a maximum. Then there are going to be 6 on the other side and 6 on the other side, giving us a total of 13. Okay. So normally, whenever they ask for the total orders, it is always going to be an odd number. Whenever they ask for the total orders, the total number of maxima formed throughout is going to always be an odd number, because there will always be an equal number on both sides of the center. Whenever you add the one which is at the center, it makes it an odd number. Okay. So the highest order maximum, for the highest order maximum, sine theta is equal to 1, and this gave us, we got n as 6.3. N is approximately 6.3. And since we said the order of maxima have to be a whole number or whole numbers, the maximum order has to be 6. If the answer to the problem had been 6.87, still the maximum order would still be 6. You don't round off to 7. Even though 6.87 is closest to 7, you cannot round off 6.87 to 7, because it means the seventh order does not fit on the screen. It will not be formed on the screen. So it's only 6 orders that can be seen on the screen. So 6 above, 6 below, plus the center would give us a total. If they wanted total orders, it would be equal to 6 on one side plus the central order plus 6 on the other side, which would give us 13. For the case described in number 6, at what angle would you expect to find the second order maximum? Repeat the calculation for the angle for n equals 3 for etc. What is the limit to this calculation? Of course, we have seen the limit is 90 degrees. So you can, I will not repeat this because it's just substituting the formula. Sine theta is going to be equal to n lambda divided by d. So you just substitute and then find theta for each of those. I expect you to get angles such as 20.4, 31, 44 point that, and so on and so forth. You cannot have sine theta greater than 1. Therefore, you would have a total of 11 maximum. not 11, but it is 13, not 11. This is typing error. We have seen that the total will be 6 on one side plus 1 at the center plus 6 on the other side, giving us a total of 13 maxima altogether. So there will be a total of 13 maxima altogether. Okay. Consider the equation d sine theta equals to n lambda. How will the diffraction pattern change if the wavelength of light is increased? So from d sine theta equals to n lambda. So n is we are saying how will the diffraction pattern change? So if d remains the same and n remains the same, it means if wavelength is increased, sine theta is also increasing, theta is also going to increase, so the angle of diffraction is going to be increased. So it means there will be more spread out. The maxima are going to be more spread out. And of course, when they become more spread out, it means they don't fit on the screen. So it means only a few of them will fit on the screen. So it means there may be few of them seen on the screen. Then the diffraction grating is changed for one with more lines per centimeter. Remember, d equals to 1 over n. More lines per centimeter means n has increased. When n increases, it means d has decreased. And notice that d is inversely proportional to sine theta. So if d has decreased, it means sine theta must have increased. And if sine theta has increased, it means the theta has increased. So it means it is also going to mean the same thing as in part A. So in part A, sine theta is directly proportional to the wavelength. So if theta is increased, so theta increases, so the maxima are going to be more spread out. In other words, if the angle of diffraction increases, it means the maxima are going to be more spread out. And because they are more spaced or more spread out, only a few of them will be seen on the screen. So there may be fewer of them seen on the screen. Then the second case I've already said, sine theta is inversely proportional to d in the first place. And I've said if the number of lines per centimeter has been increased, the diffraction grating is changed for one with more lines per centimeter. So it means n, the number of lines has been increased. And remember, d equals to 1 over n. When n increases, d must decrease because they are inversely proportional. And since d is inversely proportional to sine theta, when d decreases, sine theta must increase. When sine theta increases, it means theta also increases. So d decreases, so again theta increases, and whenever theta increases, it means the maxima are going to be more spread out, and whenever they are more spread out, only a few of them are visible on the screen, so only a few of them are seen on the screen. A student is trying to make an accurate measurement of the wavelength of green light from a mercury lamp, wavelength 546 nanometers. Using a double slit of separation 0.50 millimeters, he finds he can see 10 clear fringes on a screen. So using a double slit, he can see 10 clear fringes on a screen at a distance of 0.8 meters. So this is D, capital D for a double slit from the slits. So this is going to be slit separation is A for a double slit. The student can measure their overall width to within plus or minus 1 millimeter. He then tries an alternative experiment using a diffraction grating that has 3000 lines per centimeter. So this one is going to help us. Remember, capital N is number of lines per meter. So capital N is supposed to be 3000 times 100. So it is 3000 times 100. So capital N is going to be this 300,000 lines per meter. The angle between the two second order maxima can be measured to within plus or minus 0.1 degree. The angle between the two second order maxima, that is one above and one below. What will be the width of the 10 fringes that he can measure in the first experiment? The 10 fringes that he can measure in the first experiment. Okay, so let's first find x. So for the double slit, we know that the wavelength equals to ax divided by d. So x, the fringe width between only two, is going to be wavelength times d. This is capital D, not small d, times capital D divided by a. So the fringe separation x is going to be equal to the wavelength, which is 546 times 10 to the power of minus 9, then times d, which was 0.8, divided by a, which was 0.5, times 10 to the power of minus 3. So when I press my calculator, 546 exponent minus 9 times 0.8 divided by 0.5 exponent minus 3. So this is giving me 8.736 times 10 to the power of minus 4 in meters. So this one in millimeters, I'm going to multiply it by 100, by 1,000. So by 1,000, this is approximately 8.7 times 10 to the power of negative 1 millimeters, or it is approximately 0.87 millimeters. That is x. That is the distance separation between distance between two bright fringes. But they said he finds he can see 10 clear fringes on a screen at a distance 0.8. So if these are bright fringes and they are 10, and the distance between the two is 0.87, so I'll just multiply this by 10, and I will say the separation of 10 fringes is going to be 10 times 0.87, which is equal to 8.7 millimeters. But they say the student can measure their overall width to plus or minus 1 millimeter. So I have to round off this to the nearest millimeter. So this is going to be equal to 9 millimeters, approximately 9 millimeters. He then tries an alternative experiment using the diffraction grating. So let's now check the diffraction grating to find the diffraction grating, and the angle between the two second order maxima can be measured to within that. What will be the width of the 10 fringes that he can measure in the first experiment? So we saw that this is 9 millimeters. What will be the angle of the second order maximum in the second experiment? So of course sine theta, making theta the subject, sine theta, this is going to be n lambda divided by d, which means sine theta is going to be equal to, n is 2, the wavelength is 546 times 10 to the power of minus 9, divided by d. Remember we said n is 300,000, so this is 1 divided by 300,000. Remember d equals to 1 over n. So I'll just press my calculator here. So 2 times 546 exponent minus 9 times 300,000. Then I get the sine inverse. So the sine inverse of this is 19. So theta is equal to 19.12 degrees. But they said the angle between the two second order maxima can be measured to within The angle between the two second-order maxima can be measured to within 0 point plus or minus 0.1 degrees. So theta is the angle from the center to the second-order maximum. What will be the angle of the second-order maximum in the second experiment? So theta is going to be to within plus or minus. So this is to 1 decimal place. So this is going to be 19.1 degrees. Suggest which experiment you think will give the more accurate measurement of wavelength. So of course the diffraction grating method is going to give a better, it is going to give a more accurate measurement for wavelength because it measures the angle to a bigger precision compared to the first experiment, which measures the distance to a poor precision, as simple as that. And if we try to substitute into the values, if we try to use these angles, if I use 90 millimeters to find wavelength and I use 19.1 to find wavelength, I may get 19.5. I mean 19.1 would give a value which is closer to 546 compared to using 9 millimeters, because 9 millimeters may give a value which is relatively bigger than 546. So we have calculation gives total width of 8.7 millimeters, but with the ruler, the student measures 9 millimeters. Then calculation for the angle gave us 19.12, but the student will measure 19.1. And for the double slit experiment, a measured width of 9 millimeters for 10 fringes will give an answer of wavelength 562. You can check that. If the measured width is 9 millimeters, so it means x is going to be 9 divided by 10, which is going to be 0.9. Then using wavelength equals to a x divided by d, a is 0.5 exponent negative 3. Then x is 0.9 exponent negative 3. Then d is 0.8. So this is giving us 562. This one is giving us approximately 563 nanometers. Then when I use for the experiment of the diffraction grating, the measured second angle is 19.1, and this will give an answer of 545. We can check this. Using the diffraction grating, the wavelength is equal to d sine of theta divided by n. N is 2, so I'm just substituting. D was 1 divided by 300,000, then times sine theta, which is sine of 19.1, then divide by n, which n was 2. So this is giving me 545. So wavelength here is 545, or 5.45 times 10 to the power of minus 7, which is 545 nanometers. So you notice that this one gives a value which is closest to the answer as compared to the first measurement where the student measured the length using a ruler. So it means the diffraction grating method is more accurate. In practice, it is also much more precise because the fringes are bright. The fringes are very bright and sharp, well defined, so they are easy to analyze. Measuring the angle is easier than measuring the length with a ruler. White light is incident normal on a diffraction grating with a slit separation d of 2 times 10 to the power of minus 6. Calculate the angle between, so this is a continuation, calculate the angle between the red and violet ends of the first order spectrum. The visible spectrum has wavelength 400, this is for violet, and 700, this is for red. So we want the angular separation. So you'll find theta. I'll just give you a hint here because the formula is the same. D sine theta is equal to n times lambda. They have given us D. So you find theta, you can find the theta for red, which will be, remember n is first order, which will be small n is equal to 1. So it will be 1 times the wavelength for red, which is 700 times 10 to the power of minus 7, divide by, this is sine theta for red, divide by d, which is 2 times 10 to the power of minus 6. So it means the theta for red is the sine inverse of 700 times 10 to the power of minus 7 divided by 2 times 10 to the power of minus 6. So 700 exponent minus 7 divided by 2 exponent minus 6. Sorry, this is 700 exponent minus 9, not minus 7, because it is nano. 700 exponent minus 9 divided by 2 exponent minus 6. Then you get the sine inverse. So theta for red is equal to 20.5. I'll just substitute and find theta for violet. So it will be sine inverse of, for violet it is 400 exponent negative 9 divided by 2 exponent negative 6. Sine inverse. So the theta for violet is 11.5. So then we want the angle between violet and red. So we just subtract. So it will be 20.5 minus 11.5, which I think is 9.0 degrees. Explain why the second and the third order spectra overlap. The second and the third order spectra overlap. So let us first investigate the angles of diffraction for these ones. For red, theta for red for this, the third order maximum of violet is going to overlap with the second order maximum of red, because the third order maximum for violet is diffracted through a smaller angle than the second order maximum. We can try to verify this. Theta for red when n equals to 2. This is going to be equal to, I'm substituting the equation n lambda, so it is going to be sine inverse of n, which is 2, times wavelength, which is 700 times 10 to the power of minus 9, divided by 2 times, so divide by 2 times 10 to the power of minus 6. Then for n equals to 3 for violet, theta for violet is going to be sine inverse of 3 times 400 for violet times 10 to the power of minus 9 divided by 2 times 10 to the power of minus 6. So we want to explain why the second and third order spectra overlap. So for red, when n is 2, sine inverse, that is 2 times 700 exponent minus 9 divided by 2 exponent minus 6. Then I get the sine inverse. So this one is 44 degrees. Yet this one is going to be 3 times 400 exponent minus 9 divided by 2 exponent minus 6 sine inverse. Yet this one is 36, which is approximately 37, 36.86, which is 37 degrees. So notice that the third order maximum for violet occurs at a smaller angle than the second order maximum for red. So it makes sense for us to say that the third order maximum for violet is going to overlap with the second order maximum for red, because the third order maximum for violet light is deflected through a smaller angle than the second order maximum for red light. That's why they are actually overlapping. Two sound waves originating from the same source travel along different paths in air and then meet at a point. If the source vibrates at frequency of 1 kHz and one path is 83 centimeters long than the other, this is therefore going to be called the path difference. What will be the nature of interference? So to determine whether the interference is constructive or destructive, you look for the path difference and express it as a fraction of the wavelength, and you see if the path difference is a whole number times a full wavelength, then it is constructive. And if the path difference is an odd number times a half wavelength, or it is 0.5 of wavelength, that will always be destructive. So first of all, we find the wavelength. The wavelength is going to be equal to V over the frequency, where V is 332 over the frequency, which is 1000. So the wavelength is going to be 332 meters. Then the path difference, remember, was 83 centimeters. The path difference is in meters is going to be 0.83 meters. So to check whether it is constructive or destructive, we shall always divide the path difference by wavelength to see the ratio. If the ratio is a whole number, then it is constructive. If the ratio is 0.5, then it is destructive. So this is going to be 0.83 meters divided by 0.332 meters. So when I press my calculator, this is 2.5. Whenever you get 0.5, just know that that is destructive, because 2.5 is the same as 5 over 2 of wavelength. So it means the path difference is 2.5 of wavelength, or it is 5 over 2 wavelength, or it is 5 times lambda over 2, an odd number times half wavelength. That is destructive interference. So hence, this is going to be destructive interference. We have seen the path difference. When we divide, we get 0.5. And whenever you get 0.5, just know that that is an odd number multiple of half wavelength. Hence, it is destructive interference. Self-check. The diagram below shows a water wave on a ripple tank, which line represents a wavefront. So remember, wavefront is a section through an advancing wave where all particles are in phase. And if you recall where we started from, this is a general self-check, not about diffraction, grating. It's about summarizing waves. If you remember where we started from, a section through an advancing wave where all particles vibrate in phase. So all particles at the peak are vibrating in phase, reach the same stage in the same direction. So this is going to be a wavefront. Of course, this could be a wavelength. This could be lambda. This has no representation in waves. This could be amplitude if I draw a horizontal line through the wave. This could be amplitude. So the answer is going to be B. I'll just give a hint here. A long rope fixed at one end is being used by a student to demonstrate transverse wave. State what the student does to the rope to produce a transverse wave. Of course, this must be moved up and down. The figure below shows a section of the rope when the transverse wave is present. On the figure, show a distance labeled lambda corresponding to the wavelength. So wavelength can be the distance between two successive peaks, or it can be the distance between two successive troughs. So this is wavelength. The distance labeled A to represent the amplitude. So I will draw a horizontal line through the wave, and the amplitude is that distance there. Suggest what the student could do to reduce the wavelength of to reduce the wavelength of the wave. Of course, that is increase the rate of shaking end of the rope to increase the frequency, because if we now have more cycles, if we increase the rate of shaking and the end of the rope to increase the frequency, if the speed of the wave is the same from v equals to lambda times f, if the frequency increases, the wavelength has decreased, as simple as that. Some waves are longitudinal, some are transverse. Some waves are electromagnetic, some are mechanical. Put ticks in the table below to indicate which of these descriptions apply to the light waves. Of course, we know light is mechanical and transverse. So light is transverse, and electromagnetic, not mechanical. Then sound waves are longitudinal and they require material medium, so they are mechanical. You can always pause the video and you try to work out some of these questions just to be sure that you have picked the concepts behind waves. Two slits 0.5, so this is A. Whenever you see two slits, that is the double slit. Apart are placed at a distance of 1 meter, so this is capital D. The slits are illuminated with light of wavelength, so this is lambda. Capture the distance between the fourth and the second bright fringes of the interference patterns. Because these are two slits, it is a double slit, so you are going to use capture the distance between the fourth and the second bright fringes of the interference patterns. So remember, for a double slit, lambda equals to ax divided by d. So you are finding the distance between the fourth and the second bright fringes of the interference pattern. I think we even answered this question. So you find, let's say this is the first, the zero order, n equals to 0. You have the first, the second, the third, and the fourth. So you want the distance between the fourth. Remember, the distance between each successive bright fringe is x. So you find x. So this is the second and the fourth. So in other words, you find x and multiply it by 2. So in other words, the distance is going to be twice x. You find x using the formula lambda equals to ax over d, then multiply x by 2. Because if this is x, this is also x. In Young's double slit experiment, the eighth bright fringe is formed 5 millimeters away from the center. It is the eighth. When the wave of the light used is 6.2, capture the separation of the two slits if the distance from the slits to the screen is 80 centimeters. So this is capital D. And this is the wavelength. And they want you to capture the separation of the two slits. They want you to calculate A. They have said the eighth bright fringe is formed 5 millimeters away from the center. So if this is the center, this is 1, 2, 3, 4, 5, 6, 7, 8. X, 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 X. So those are 8 X's. 1, 2, 3, 4, 5, 6, 7, 8. Because this is n equals to 0 and this is n equals to 8. So it means x is going to be 5 divided by 8 in millimeters. I think we have also answered such a question. A progressive and a stationary wave each has frequency 240 and speed 80. Capture the phase difference between two vibrating points in the progressive wave, which are 6 centimeters apart. So we know that phase difference equals to 2 pi into x divided by wavelength. So you can just find the wavelength from V divided by frequency. So using V divided by frequency, you get the wavelength, and then sub x is equal to 6. So substituting in the wavelength, you should be able to get that value there. A string is stretched between two fixed supports by 1.2 meter by 1.2 meters. Stationary waves are generated on the string. It is observed that the two stationary waves frequencies are 180, 135. There is no resonant frequency between these two. It means these two are consecutive, one after the other. The lowest resonant frequency of this, calculate the lowest resonant frequency. Remember what we did for these frequencies. If it is a string, Fn equals to n times F naught. If this is the first one, the next one, these ones differ by 1, so the next one will be Fn plus 1 equals to n plus 1 into F naught. So you can say Fn is 180 and Fn plus 1 is 135. No, I want to do it the other way around because 180 is bigger. So let this be 135 and let this be 180. So 180 is equal to n times F naught plus F naught. So you have this equation and this equation. You calculate. You can now subtract to find F naught. We did an example to that. Then the speed of the progressive wave on the stretched spring. So if I have F naught is V over 2L for a stretched string. So if I know the length as 1.2, I will just substitute and get FL. Let me find F naught here. This is the last question I'm solving, I think. So when I subtract this equation here minus this equation here, I have that F naught equals to 180 minus 135. So F naught is going to be 45 hertz. Then it means V is going to be F naught times twice L. 45 times 2 times L, which is 1.2, which is 108 meters per second. A source of sound of frequency 2000 is placed in front of a flat wall. When a microphone is moved away from the source towards the wall, a series of maxima and minima are detected. Explain what has happened to create a maxima. Of course, a maxima that is constructive and a minima that is destructive. So you should be able to explain that. We did this in one of the lessons. The speed of sound in air is 340. Calculate the distance between successive minima. The distance between a minimum and a minima is always half of wavelength. So they have told you the speed is this, and we have the frequency. The wavelength is equal to the speed over the frequency. The distance between two successive minima is half wavelength, or the distance between two successive maxima is half wavelength. So if I can find the wavelength, then I should go back and get half of the wavelength. That is going to be the distance between successive minima. A string is stretched between two fixed supports, 3.5 meters apart. Stationary waves are generated by disturbing the string. One possible mode of vibration of the stationary wave is shown in the figure below. The nodes and antinodes are labeled N and A respectively. Distinguish between a node and an antinode. Of course, by this point, you know what a node is: a point where particles are permanently at rest, and an antinode, a point or region where particles vibrate with the maximum amplitude. State the phase difference between the vibrations of particles of the string at any two neighboring antinodes. So particles here and particles here, these are two neighboring antinodes. We say this is the particles in one segment vibrate in phase with each other, but they vibrate 180 degrees out of phase with the neighboring particles. So the answer here is 180 degrees or pi radians. Particles between two neighboring nodes vibrate in phase. The phase difference would be 0. But particles between two neighboring antinodes vibrate 180 degrees out of phase. Calculate the ratio of the frequency of the mode of vibration in the figure above to the frequency of the fundamental mode of vibration of the string. Remember, for fundamental mode, we have only one cycle. I mean half a cycle, which is one loop. For the fundamental mode, F naught was equal to V over 2L. This one is 1, 2, 3, 4, 5. Someone will be able to notice that this is going to be F5. This is F5, which is going to actually be 5 times V over 2L. In other words, the ratio here is going to be 5. because this is 1, 2, 3, 4, 5. For the fundamental mode, we have only one loop. So this is going to be 5. The frequency of the mode of vibration shown above is 160. So it means F5 equals to 160. Calculate the speed of the progressive wave which produced this stationary wave. Remember, these are 5 cycles, 1, 2, 3, 5 loops, 1, 2, 3, 4, 5. And the length was 3.5 meters. So this is going to be 5 times V divided by 2L. Or if you want, you can derive this. F5 equals to, frequency equals to V over wavelength. This is 1 cycle, 2 cycles and a half, which is 5 lambda. So L is equal to 5 over 2 lambda. So lambda is equal to 2 over 5 of L. So this is how, when you substitute into frequency equals to V over lambda, it becomes 5 over 2 L times V. That's how I got this. But L was 2. So this means V is going to be 160 times 2 times L, which is 3.5. L was 3.5 divided by 5. So 160 times 2 times 3.5 divided by 5. So V is going to be 224 meters per second. You can also verify that. My calculations may not always be clear, but this is a self-check where I just give you a hint. You can always pause the video and try to solve these questions. A vibrating tuning fork of frequency 340 is held over the open end of a resonance tube. The other end of the tube is immersed in water. The length of the air column is gradually increased until resonance first occurs. Taking the speed of sound in the air to be 340, calculate the length of the air column. So you should try this because I gave an example. We can hear sounds round corners. We cannot see round corners. Both sound and light are waves. Explain why sound and light seem to behave differently. I've also explained this. State the features of a stationary wave that distinguish it from a progressive wave. So for a stationary wave, different amplitudes. Amplitude varies from 0 at the nodes to maximum at the antinodes. Yet for a progressive wave, particles have the same amplitude. We have nodes and antinodes in a stationary wave. Stationary wave transfers energy. No energy is transferred in stationary waves, yet it is transferred in progressive waves. We have also done this. A string 75 centimeters fixed at one end, the other end is moved up and down with a frequency of 15 Hz. This frequency gives a stationary wave pattern with 3 complete loops. So that is 1, 2, 3. So this is F3. Note that is 1.5 cycles. Calculate the speed of the progressive wave which interfered to produce the stationary wave. So it means F3 is equal to 15. And the length here is 75 centimeters. So you know what F3 is, or you can derive the relationship between the frequency and the length of the material. We have done this in the examples, but maybe I can show that. So L is a half plus a half plus a half, 3 halves, that is 3 over 2 of wavelength. So wavelength is equal to 2L over 3, and the frequency is equal to V over lambda, which is going to be V over 2L over 3, and the 3 goes up, so it is 3V over 2L. But remember, the frequency was 15, so I just equate this to 15. So if I make V the subject, V is going to be 15 times 2 times L, which is 0.75, because it was 75 centimeters. Then I divide this by 3, which I think 15 times 2 times 0.75 divided by 3. This is approximately 7.3. So it is 7.3, not 7.5. It is 7.3. A violin string vibrates with a fundamental frequency of 440. What are the first frequencies of its first two overtones? So F1 is equal to F0, which is equal to 440. Remember, for a string, Fn is equal to n times F0. So you can find F2, you can find F3. So 880, 440 times 3, 1320. And so on and so forth. Why do I feel like I pressed a calculator wrongly here? 15 times 2 times 0.75 divided by 3. No, this answer was correct. 7.5 was correct. Sorry. So find the fundamental frequency and the first two overtones for an organ pipe, length 0.17 meters and closed at one end. The speed of sound in air is 340. I think we have answered a similar question. You can try it out. The speed of waves on a certain stretched string, whenever it is a stretched string, you know that Fn is equal to n times F0. When the string is vibrated at a frequency of 64 Hz, stationary waves are set up. Find the separation of successive nodes in the stationary wave. Remember, the distance between a node and a node is equal to half of wavelength. So you just use this frequency and the speed to find the wavelength, because wavelength is v over lambda, over f. Then distance is half wavelength. You can make an empty lemonade bottle resonate by blowing across the top. What fundamental frequency of vibration would you expect for a bottle 30 centimeters deep? So L is 30 centimeters deep. So you can think about this as a closed pipe. The speed is 340. So you want the fundamental frequency. So think of a closed pipe and think of a fundamental frequency. So the fundamental frequency F0 is V over 4L. We have derived this in one of the lessons because this length L is representing a quarter cycle. So V is given, L is also given as 30. You just change it to meters and substitute. A certain organ pipe closed at one end can resonate at consecutive frequencies 640, 896, and 115 Hz. Deduce the fundamental frequency. So we have seen that closed pipes are the frequencies differ by n equals to by 2. So if the first one is Fn equals n times F0, the next one is going to be Fn plus 2, which is going to be n plus 2 times F0. So I will use the first two. If the first one is equal to 640, and the second one is equal to 896, so I'll just substitute and subtract them. So I'll say 896 minus 640 is equal to n times F0, cancels out with n times F0, so I remain with it twice F0. So I'll say 896 minus 640 divided by 2, which makes this correct. I think we have done this question earlier on. A ripple tank is used to demonstrate interference between water waves. Describe the apparatus used to produce two sources of coherent waves that have circular wavefronts. So the apparatus used to produce two sources of waves, I think we have demonstrated this earlier on. that are coherent. You could use slits. You could use two slits, or you could use two dippers, and so on and so forth. A wave pattern produced in A is shown. Solid lines on the figure represents crests. Draw two lines to show where maxima would be seen. So maxima found at points where the crests are meeting. For example, 1, 2, 3, 4. So I will draw a line through these ones. Or you could choose another point. So for example, you have 1, 2, 3, 4, 5. You maximize. So these are lines. I could draw a line here. That's where maxima form. Label this X. So that is X. Then draw one line to show where minima would be seen. Of course, for minima, we have a crest meeting a trough. Between two crests, we expect there to be a trough. For example, here, I'll just choose simple points. So, for example, there could be, let's say I'm considering this as as a wave. Its crest is meeting with, okay, between every two maxima, there's a minima. So this is a maxima, a crest for the other wave, and this is its second crest. But between them, there is a minimum, there is a trough. So this one is a trough. I mean, this is where the trough of the other wave. Let me try to sketch the other one. This is going to be its trough. So it meets here, it meets there. I can do another trough here. So it is also meeting somewhere here. I can draw another trough here. Between two crests, there is a trough. So it is meeting here, and so on and so forth. So I'll now rub off the troughs that I've drawn. So I'll just draw a line through these points. Okay, so these are approximately somewhere between. That's where we have destructive interference when a crest meets a trough. So it is somewhere between. And so on and so forth. And I would label this N. You can do something better. And lastly, a long tube is open at one end. It is closed at the other end by means of a piston that can be moved along the tube as shown below. A loudspeaker produces sound of frequency 550 Hz and is held near the open end of the tube. The piston is moved along the tube and a loud sound is heard when the distance L between the piston and the open end of the tube is 45 centimeters. The speed of sound in the tube is 330 meters per second. Show that the wavelength of sound in the tube is 60. So I think this one is direct. Wavelength equals to V over lambda, over F. 330 divided by 550, and I think this is 0.6 meters, which is 60 centimeters. I think that is correct. On the figure, mark all the positions along the tube of the displacement nodes. Label these with the letter N. The displacement antinodes, label these with the letter A. Note that length is 45 centimeters, but the wavelength is 60 centimeters. So in the figure, we are going to mark all positions along the tube where the displacement nodes are formed and where the antinodes are formed. Of course, we know must be an antinode here at the open end, and there must be a node at the closed end. That is 1. However, remember the distance between antnode and a node is equal to a quarter of wavelength. The distance between an antnode and a node is a quarter of a wavelength, which is going to be 60 divided by a wavelength, 60 divided by 4, and this is 15 centimeters. So it means between for every 15 centimeters from an antnode, we must have a node. And remember, the length was 45 centimeters. So 45 is going to be divided into how many quarters? So 45 divided by 15 is equal to 3. So 45 divided by 15 is equal to 3. So after every 15, we must have a node from the antnode. So this is going to be, we are going to divide this length into 3 parts. So this is going to be 1, and this is going to be 2. Because the distance between node and antnode is going to be so let me check this. This is a quarter cycle. No, this is not going to be correct. Because the distance between a node and an antnode is going to be 15. So this is not going to be true. So it means we have only, remember, for an open pipe, for a closed pipe, the number of nodes is the same as the number of antnodes. Since we have an antnode here and a node here, the distance between an antnode and a node is a quarter cycle. The distance between an antnode and the next antnode is going to be 30 centimeters. So if I have one antnode here, after 30 centimeters, I should have another antnode. So it means there's only one node here. So it will mean I will have something like this. So this is the second antnode. The next must be a node. Antnode, node, antnode, node. The number of antnodes is the same as the number of nodes. So you have a node here, antnode, a node. Of course, between antnode and node is 15 centimeters. Alternatively, you can divide this length into 3 parts. And after every part, when I start with a node, after the first part when I start with an antnode, the first part I put a node. The next third part I will put an antnode, and then the last one will be a node. The frequency of the sound produced by the loudspeaker in A is gradually reduced. Determine the lowest frequency at which a loud sound will be produced in the tube. The lowest frequency is the fundamental. And the fundamental frequency F0 is going to be formed when F0 is equal to V over 4L, because it will be a quarter a cycle. For the fundamental mode of vibration, remember we have a quarter of a cycle in the length L. So L is equal to a quarter of a wavelength. So the wavelength is going to be 4L. So this will be equal to V, which is 330 divided by 4 times L, which is 0.45. So 330 divided by 4 times 0.45. So this is approximately 180 or 83 hertz, or 183 hertz. Yeah, this is two significant figures. Okay, so I think that would be the lowest, and I would like to stop waves here. In the case of any mistakes, I can always make some mistakes. I have no problem with that. I'm not an island. Some things I have to make mistakes. I might press my calculator wrongly. You can always correct them. Until next time, bye bye.